I think we can go ahead then. Hello, everyone. My name is Abraham. As you probably know, my talk is going to be about continuous integration and continuous deployment and how to make it fast and why. So I'd like to start by introducing myself and talking a bit about me. I work for Equal Experts, which is a company that contributes or helps clients, other companies to try to help them develop new products or fix particular problems or challenges that they may be facing. At the moment, I am doing an assignment. I am working with Mendeley, which if you're in the research space, you probably have heard of them. In Mendeley, we're doing different kinds of products for researchers to try to manage their papers, their references, their quotations, etc., etc. I am also a Java editor at InfoQ. If you know InfoQ, then you probably know what kind of news we publish there. If you don't, then go and check. I've also collaborated a couple of times with O'Reilly. I've done a webcast, also a couple of articles, and I recently wrote a small book that is about to be published. I'll let you know more once it's actually out there. Finally, I'm an associate at the London Java community, which basically means I help run it. We help with the different events. We help with community activities, try to support, etc., etc. In my free time, which is not much, I like to look after my plants. So that kind of Sylvatic-looking thing, it's I have some sunflowers here, lavender, parsley. That's meant to be broccoli, although it has gone a little bit wild. And that thing with loads of flowers is actually thyme, but it seems it's a plant, so it produces flowers too, which is very amazing. Also, I like running, and in fact, I'm going to abuse of your kindness a little bit. I have a couple of runs lined up, and I'm raising funds for charity for them. If you're interested in knowing more, that's a link for the British 10K that I'm running in July, and that's a link for the Royal Parks Half Marathon that I'm running in October. If you'd like to know more, just take a picture or copy those links or see the recording later. If not, then that's fine. We can just move on. Right. Now, I'd like to start by providing some kind of common background of what I mean when I say continuous integration and continuous deployment. The reason I want to do this is because different people understand different things. So first of all, continuous integration, from my point of view, is just checking that everything is working after a commit. So you commit, and then what you do is you rebuild all your stuff, and you run your tests, and you make sure everything is well. And continuous deployment is basically the same thing, but also once you finish the process and you create a package that you can release to some environment, production, testing, whatever, or at the very least, it's a package that is releasable, so you can actually release on demand as you like. Right, so whenever I talk about continuous integration and continuous deployment, this is what I'm going to mean. Right, about the talk itself. This talk is going to be divided in 3 parts. Yep. First, I want to talk about why we would like to have fast continuous integration or continuous deployment. Right, because probably you've seen many talks, and in different talks you've seen about things that you could be doing. And I think the most important thing to know is why you should be doing those things. Probably you are not going to have time to do all the things you're going to discover at DevOps, so you're going to have to pick. The second part is going to be how we're going to do this. As this graph is probably giving away, the whole point is about breaking things down into smaller builds that are interconnected, but more on that later. And then finally, we're going to take a look about where we go from that. Why are we doing this? Let's do a first quick show of hands. Who has any kind of continuous integration or continuous deployment environment? Good. Wow. I think you all know what I'm going to say. Anyway, let's try to set a background. Imagine I have a build, one build, that produces a web application. In this case, I'm going to call it the super app. And because I'm a little old school, my artifact is going to be a WAR file, because I still use Tomcat and things like that. But that's not important. What is important is that it's kind of the beginning of my app. So it's relatively small. It only has about 75 files, 800 tests, and the whole thing takes about 4 minutes. These numbers are completely made up, but you will get the point. The thing is, I continue to develop my applications, and obviously it grows. And it grows, it has more files, more tests, and obviously it takes longer. And then that continues. Until at one point, it's going to get too big. So now let's do a little survey. Who has a build that takes 10 minutes or less to run? Quite a few people, that's good. Between 10 and 30 minutes? Between 30 minutes and 1 hour? Good. More than 1 hour? Yeah, there are always a few. Now, why is that bad? Here's the thing. When you have a build that takes very long, then that means that you have to sit there and wait to know whether your change broke anything or not. And if you have to wait 10 minutes, that's probably fine. You can just check Reddit or your mail or anything like that in that time. But if that build takes 1 hour, eventually you're going to get bored. You don't want to be sitting there waiting for an hour before you know you can carry on. So what is going to happen is that eventually you're just going to move on, right? Slot feedback is not good. Now, when you move on, two things can happen. One is your build is green, everything is working, that's fine. Or your build is not green. Now, if your build takes an hour, then if you're lucky, it's going to break at the beginning. If you're not lucky, it's going to break at the end. Chances are it will break halfway, so it will take about half an hour for you to know that you broke something. In that half an hour, you probably moved on. Your mind is already on something else, and now you have a red build. And you face a dilemma, which is, I could just carry on with what I'm doing and worry about the build later, or I could stop what I'm doing and look after the build. Now, chances are, if you're like me or like many people, you don't like changing context. So then when you leave what you're doing to look at the build, probably you just want to get rid of it. So what you're going to do is you're going to take a quick look. Oh, yeah, it's probably this. You do a quick fix. You submit the quick fix. And then you make a mental note and say, once I finish what I'm doing, I'm going to go back to this and make a proper fix. OK, so that goes in. And then if you're lucky, your change fixes problems. If you're not lucky, the build's still red. And now you don't know if maybe your fix was a bit rushed and actually it didn't fix the problem and that's why the build's still broken. Or maybe your change actually fixed the problem that you had, but also you created some of the problem because you did it too quick and you didn't analyze things. Or maybe your fix is perfectly fine, and what happened is that in the time that the build was red, somebody else in the team made a change that broke things. And actually the build is broken now, not because of you, but because somebody else, right? At this point, you just don't know. That's the second problem that we have. So I guess everybody has been in a situation like this before, and usually what happens is that you start talking to the other guys and go, OK, who made a change? What did you change? Is it this? Is it that? And then you get into a bit of a change frenzy. Everybody starts fixing things very quickly. Oh, I'm just going to fix this. Oh, it's just this. I'm just going to put this in. And it doesn't work. And everybody's just trying to fix and stepping on each other's, and it doesn't work. And then eventually, one of the developers stands up and go, all right, everybody stop. Nobody makes any commits until I fix the build. Once the build is green, then you can carry on working. Has anybody been in a situation like this before? Yeah, exactly. It happens. Now, these are bad enough, in my opinion. However, you could say, some people could say, well, this is just annoying, but it's part of the life of a developer. You know, there are ups and downs, good and bad, and this is just the bad side. But sometimes these annoying parts could actually be impacting your business. For instance, does anybody have an SLA? Something that you have to fix within a particular time? Good. There's some people here. So sometimes you're in a company that you're producing software for somebody else, and you have some kind of contract that says, if we find a critical bug, you need to provide a fix within 5 hours, something like that. Now, if your build takes 1 hour, that means you only have 4 hours to fix it. And the longer your build takes, the shorter you have. Eventually, you can't meet your SLAs because you just don't have enough time to do it, which means either you need to have shorter SLAs, longer SLAs, or you have to accept the fact that you don't meet them. And then eventually your client might say, you're not providing what I need, I'm going to go somewhere else. So you might be losing business there. And then finally, there's another thing, which is even if you don't have SLAs, there are some companies out there that are experimenting with kind of, let's say, reactive programming. And by reactive, I don't mean reactive in the reactive streams way. I mean, they try to write code, or they try to make changes that reacts to actual events in the world. For instance, there's the Eurovision night, and a particular singer comes out with a particular outfit, and they go, well, you know what? If we change the website, making some sort of user experience around this particular singer that was very popular, we actually managed to get traffic because people are in the mood, people are all talking about it, they are tweeting about it. So if you manage to put something on the web, everyone will come in. Now, the problem with that is that since it's a very spur of the moment thing, the longer it takes for you to make that new user experience around something, the less that makes any effect. So if you take too long, then it doesn't make any point. So then obviously, if you need to react within, say, 2 hours for that to make an effect, if your build takes an hour, again, you only have 1 hour to design a user experience, make it, test it, and put it in production. So those are pretty much the problems that I can think when your build takes too long. And you probably have some others in your mind. And if you do, please let me know later, because I like collecting these things. Now, I've been talking around with many people, and both when I was working at companies with clients and both when I was talking to colleagues about how different people manage to fix these problems. And I found several answers that I didn't quite like, to be honest. The first one is people just suck it up. They say, yeah, it's bad, it's long, what are you going to do? Live with it. I didn't like that. The second thing people try to do is they try to split the test. So they go, OK, hang on. We have quick tests, like unit tests, and then we have slow tests, like integration tests, the end-to-end, the ones that spin up the database and all the stuff, right? You probably have heard about the famous, the ice cream cone of testing. Yeah, so a bit like that. And when they decide to do is, OK, we're going to do continuous deployment only with the unit tests. So on every commit, we build and run the unit tests, but not the integration tests, because that's too slow. And what we're going to do is we're going to schedule the integration test to run at night. Now, it's true that that kind of makes the build faster, but at the expense of not really knowing whether things work. So if before, maybe you took an hour to find out whether you broke anything, now you're going to take a whole day, because maybe you don't find out until tomorrow morning when you come to the office and you see that overnight the tests were failing. And maybe you don't have one now, maybe you have 5, and that's going to be even harder. There's another technique that people apply, which is they just split the product. So if you have an application that has a build that is too long, what you do is you maybe split it into 2 different applications, you give it to 2 different teams, and then they are completely separate entities. Team A develop their part, and they do continuous deployment on their part. Team B develop their part, and they do continuous deployment on their part. But you don't put the 2 things together until you actually have to do a release or something like that. Now, that means you don't take 1 hour to find out whether things work. You don't take 1 day. You maybe take weeks, which is the long that it takes for the 2 different components to actually be put together. Which is, again, not something that I quite liked, because you're losing the benefits of the tight feedback that continuous integration and continuous deployment give you. And then finally, the last kind of measure that I found, it's in a way the funniest one, is what they call a test deprecation policy. Has anyone heard of this before? Good. Basically, test deprecation policy means, OK, let's check in Jenkins or TeamCity or whatever build system we have. And let's analyze the tests that we run, and let's check the ones that don't fail or fail very rarely. Right? And we have this bunch of tests. And then the theory goes, well, if they never fail, that means they're testing a part of the functionality that is very stable, which probably means it's never going to fail, which means we can just delete the tests. And that way, the build will be faster. Yeah, but that's a bit like saying, you know what, these roads, we don't have accidents here. They seem very safe, so maybe we don't need helmets or safety belts or anything like that, right? So again, I didn't like that idea very much. Now, what do I like? That's the next question. As I was saying before, the idea that I pursued was you have one big build, break it down into multiple independent but connected builds. And the connected build, the connected part is essential. So for instance, if this is my super application, what I'm going to do is I'm going to split it into two. Maybe I get a backend that I spin off, right? And then I have two different builds. That one takes about 4 minutes, and that one takes about 6 minutes. But here's the crucial part. Whenever I make a change here, I build an artifact that I store and version somewhere. And then immediately after I build this, I trigger a build of this that will consume that artifact that I just produced, and then run all the tests, and if it works, then produce the final WAR file. But if I make a change in this module here, I don't rebuild that part. I just consume the existing jar file that I have stored somewhere. And that way, I don't need to run all the tests. I only run these tests here. And if any of these is too big, then I break it down again. And I create that network that I showed you before, where I have a lot of interconnected builds, and the continuous integration system knows which ones it has to rerun after each change. Okay? Does anybody have a system like this? I've seen it in a few places. Okay, a few, that's good. Now, if you don't have it, I could tell you a way to actually build something like this. Unfortunately, we don't really have enough time in this talk for that, because it's actually a talk on its own. But if you're interested, you can take a look. This is another talk that I gave called Scalable Continuous Deployment with Maven, in which I describe one way where it's a pattern way where you can keep on breaking down your builds and creating connections between them. So then when you run one, it will rebuild that one and the ones that I need to rebuild, but only those ones. And then you will achieve this effect of just having a network of interdependent builds. Can I wait a second just in case anybody else wants to take another picture? Okay, so at this point, I'm going to assume that you have something like that, because that's the first step. You have one big build, you break it down into smaller ones. Now, the tricky part comes that at the beginning, it's kind of easy if you know how to do it, because you have one big build, you break it down. When you have two builds, one connected to the other, and if it's still slow, well, you get the biggest one of the two and you break it down. But the moment you have a network of maybe 30, 40, 50 different builds, and the whole thing still takes too long, it's going to be a bit harder to know what you have to change to make the whole thing faster, right? Because now you have a very complex things with many parts that interact with each other, and it's a bit difficult to get your head around the whole thing. Now, this is where it gets to doing proper performance analysis of your build system. Now, if you're doing performance improvements of an application, usually what you do is, you can just go to the code and start making changes here and there, assuming that it's going to be faster, or you can actually establish a metric, establish a number of ways to measure the performance of your application, establish some thresholds. Maybe you say, well, this particular operation should take 300 milliseconds or shorter. And then what you do is whenever you go beyond your thresholds, then you start making changes to see if you can go back to your measure. So that's kind of what we have to do with our continuous integration or our continuous deployment system. Now, let me show you how to do that with a real case. This is a system that was originally one big build, and then we broke it down into all these many pieces. We created 3 different WAR files for 3 different web services. It was a Maven-based system. So in fact, we have a parent POM over there. These arrows here mean that these triggers every build, or conversely, that everything depends on that one. I just drew it that way because otherwise having too many arrows would be not very nice. Also, this is just a login library, and pretty much everything depends on the login library. That's why it's drawn that way. And then the rest is kind of self-explanatory. These builds has these two as dependents. That means when you change this one, then you need to trigger the other two, etc., etc. This was broken down using the technique that I mentioned in the other talk, so you can take a look at that. Now, here's where I started the analysis. First of all, I wanted to know what needs to be rebuilt. So then for that, what I did is I took 2 months worth of subversion logs, and I analyzed where the changes were going. And it turns out that in those 2 months, 28% of all changes went to that particular module over there. Now, it might sound like a lot, because that's over a quarter, but on the other hand, when you're working on things, you tend to work on related features, one after the other, right? You don't work on one thing today, and then tomorrow on something completely unrelated. I mean, sometimes you do, but usually that's not how you work. You work on related things. And if your architecture makes a little bit of sense, then those related things will concentrate in the same modules. So yeah, over 2 months, about 28% of all commits went there. Now, that means if 28% of all commits go here, I need to rebuild that 28% of the times, but also I will rebuild those two 28% of the times, because whenever I change that, I have to rebuild this. If you're strict, it will be slightly less, because sometimes that build will fail, and if it fails, you don't trigger the other ones, but well, for this purpose, we can say it's the same number. Okay, now I checked what the next most changed module was, and it turned out to be that one on the top with 20%. And again, if that one is modified 20%, then every time that triggers, this one triggers too, which means that one is rebuilt 48% of the time. Okay, this is good. This kind of shows that splitting things saves you time, because these 4 builds here concentrate about half the commit. So half the time, the whole system is remaining as it is. You don't have to rebuild it. You don't have to retest it. So that's good. But more importantly, if you continue this exercise of measuring the percentage of time that is rebuilt in all the modules, you could create kind of like a temperature graph that shows builds that are very hot, as in builds that you have to rebuild a lot, and builds that are cold, that are very stable. And in my case, with this system, it looked like this. And you can already see a few interesting things. For instance, the WAR files are by far the hottest things, which makes sense because whenever you change anything, eventually you're going to have to rebuild at least one of the WAR files. The parent POM and the logging library, they're rather cold, which makes sense because you shouldn't need to change such basic things very often. And then you have a bunch of things in the middle that have various colors. So for instance, let's take a look at this one here. Its color compared to its dependency, it's relatively warmer, right? That one is kind of blue, that one is sort of purple, which means this one is being built more times than that one. Now, if we change that, we're going to rebuild this, which means that if this one is being rebuilt more times than that one, is because we're making changes, we're making commits to this particular module, right? Now, let's compare that one to its dependencies. They're roughly the same color. That means that we are rebuilding all this roughly the same number of times, which means the reason we're rebuilding all these 5 bubbles here is not because we're changing them, it's just because its dependency is being modified. So we have one build here that seems to be receiving a number of commits, considerable, and that has a lot of dependencies that have to be rebuilt as a result. So this kind of graph is already telling us that maybe that thing here is the root cause for a lot of the rebuilds that we have in our system, and therefore for a lot of the time that we keep rebuilding. Okay, that's good. Now we can go one step further. I have shown here the frequency at which things are rebuilt. Let's add another dimension. Let's take a look at how long those builds take. So we can get these bubbles and size them according to the duration of the build. And it looks like this. Again, a couple of obvious times, WAR files, they're huge, because in our case, you have to package the WAR files and you have to put them into Tomcat, or well, that's what we did. We did put them into Tomcat, and then we ran integration tests. And the integration tests, they are usually longer than the unit tests that the other ones have. The POM file tiny thing because it doesn't even compile anything. It's just an XML. It checks that the syntax is correct and then puts it, in Artifactory. And then again, look at this one. It's not huge, but it's bigger than the ones around, which is kind of giving us weight to the idea that maybe there is a lot of things in that module. So if I was to look at this and I thought, my build is too big or my build is too slow, I need to make it faster, judging by this, I would say maybe what I have to do is split that. Maybe what I can do is, there are too many things depending on it. Maybe I can split it. So some of the things depend on one of the modules, some of the things depend on the other module. And then, first of all, the two of them will receive fewer number of commits. And when they do, they will trigger fewer number of builds. And then overall, the whole thing will be faster. Yeah, does that make sense? OK. So that's good. That's useful. Now, the problem with that statement is that it has an if at the beginning, which is if my build is too slow. So then there comes another question. How do I know if my build is too slow? Because all this that I've done is relative. Frequency is relative to each other. Size, again, too big or too small is relative to each other. These bubbles look very big. But if that meant 1 minute and that meant 20 seconds, that's fine. So then the next thing we need to do is we need to start measuring things in our system overall. Now, what I'm going to do now, it's going to seem a little bit dry because it's going to be like defining metrics and pseudo formulas and stuff like that. But bear with me because I think it's going to make sense in a moment. So the first metric that I like to define is what I call the build time, which is basically how long a build takes to execute. And the second one is the change rate, which is how often I make changes to a particular module. OK? So if we take a look at the graph that I showed before, the build time will be the size of the bubbles. The change rate is not the color in this case, because the color is the rebuild time. But we rebuild something not necessarily because we're changing. So the change rate would be this 28% that I talked about at the beginning. OK? So we have two of them now, the build time and the change rate. OK. Now, imagine we have a system like this with dependencies. So A, and then when A is done, it triggers B and C. I'm going to define the impact time as the total time that it takes from the moment I make a change to A to the moment all the builds that are triggered as a result are cleared. Right? So if I make a change to A, obviously I'm going to have to build A, but then also I'm going to have to build B, and I'm going to have to build C. And if B and C have further dependence, then I'm going to have to build those as well. So the impact time of A is the result of all that being built. OK. We can sort of calculate the impact time of A by using the build time, although that will depend a bit on whether we have parallel capabilities in our build. So simple case, let's assume we can only build one thing at a time. If that is the case, we have serial execution, and the impact time of A will be the time it takes to build this, plus the impact time of B, and plus the impact time of C. Right? Obviously, if you have no dependencies, then your impact time, sorry, no dependence, your impact time will be the same as your build time, and that's how you can keep calculating these values from the end of the graph back to the parent. Now, if you have a build that can run things in parallel, then your impact time will be the time it takes to build A, and then whatever it takes longer from the other two. OK? Now, again, this is a bit of an approximation, because sometimes your restrictions might be a bit more complicated. For instance, you might be able to run builds in parallel, but only up to a point, because you have, say, 4 slaves. If you have 4 slaves, then you can run up to 4 builds in parallel, but no more than that. Also, sometimes you have builds that depend on shared resources. And when one of them is using the shared resource, the other ones cannot execute. And that's, again, going to change this. But it's an approximation. This is just a way to measure things and give you an idea of where to go next. So this, for instance, if we think of the impact time here, oddly enough, the impact time grows as you go to the left. The impact time of these builds will be exactly the build time. But then this one here is going to include, as its impact time, this build time. And then this one here is going to include those two, etc. So then in the end, the build that has the highest impact time will be the POM, because everything depends on it. Whenever you change the POM file, everything has to be rebuilt. Now, that makes us think one thing. The fact that a build has a high impact time, is it a problem if you don't change it very often? Right, so then we have to combine the impact time with the temperature. And with that, we create what I call the weighted impact time, which is basically the impact time times the change rate. And then this way, we're going to balance how impactful a particular build is and how often we actually run it. And then that's going to give us a way to compare how much each of the individual modules contributes to the overall time of the build system. And then finally, we can combine all the different weighted impact times together to create the average. And what this is basically going to tell us is, on average, when you make a change, a commit anywhere in your system, how long does it take to clear? For many people, this will be the metric that you're going to be looking after. Because maybe what you want to say is, on average, I want my build to take 10 minutes. If sometimes it takes longer, that's fine, as long as my average is still 10 minutes. If my average goes above 10 minutes, then it's going to start. Then is when I'm going to start looking at the temperature maps and things like that to try to figure out what do I have to change to make things faster. Now, I mentioned you can use the average impact time as your threshold, right? Because it can tell you, well, on average, this is how you work. Now, maybe in your particular organization, you're not so worried about the average. You're worried about maximum. For instance, because, as we said before, you have an SLA. You have to make sure that you provide a fix within 5 hours. So you don't want your build to take ever longer than, say, 30 minutes. Then what you would do is you will look at the maximum impact time. So you will continuously measure the impact time of all your builds. You will get which one is the highest, and you will monitor that and make sure that it never goes beyond your threshold. And if it ever does, that is when you start looking back and looking at all the different variables and the maps and the graphs and saying, okay, what do I have to change to get this back to 30 minutes? Sometimes you can't afford to look at the maximum impact time of the whole thing, but there are some very critical modules that they do have to be quick to rebuild. For instance, maybe you have a very large web application, and most of the time it's kind of, it's just games, it's silly. If you have a bug in a game, it doesn't really matter that much. But you have a payment module that manages credit cards and stuff like that. Now that has to be quick. So maybe what you want to measure is not the maximum impact time of everything, but the maximum impact time of some particular modules that are critical to your business. You can do that, but if you do that, be careful, because sometimes the problem will not be in the module or in the dependence, it will be in its dependencies, which means sometimes to be able to measure the maximum impact time of a particularly critical module, you're going to have to keep looking back at the dependencies. Now, I said it was going to be a little bit dry. Sorry about that, but I hope it made sense. I'd like to reflect a little bit on what we said. So let's go back to the temperature map. Now, we do this taking into account how often things are rebuilt. How often things are rebuilt are driven by two variables, basically. One is the interdependencies of the modules, right? If this one depends on that one, then that one is going to be rebuilt if that one is rebuilt. But it's also driven by what I change. If I make a lot of changes here, then all these sections will have a particular color. If I make color of changes here, then this section will have colors. That means that the temperature map is going to be different depending on what the team is working on a long time. Which also means that your bottleneck is going to be different depending on what you're working on. Now that's interesting because the whole thing that we're talking about is if I find that this is too build, then I just split the module, which basically means we're changing the architecture of the application, etc., etc. But then what we're saying is that the optimum architecture today is not necessarily the optimum architecture in 2 months when we're working on something different and our pattern of changes goes somewhere else in the system. Which means that maybe today we think, this is the architecture we need. We're going to reshuffle the modules this way. And in 2 months from now, I need to undo all I did because what was a good decision back then, now it's a bad decision and it's making my build slow. And maybe I had to break down builds and now I had to put them together again, right? So that kind of forces us to have a bit of a change in the mindset. I think architecture traditionally was a rather static thing. Many people would do it even before the business exists. Before the product or the application exists. There will be people on the whiteboard and there will be people on paper doing diagrams and saying, this is the architecture, this is how we're going to split the modules. And now we're saying, okay, you can do that, that's a good start, but that's not the end of it. Your architecture is dynamic. Depending on how your build system behaves and depending on how you're making changes to things, you're going to have to be continuously adapting your architecture to make sure that it stays up to the new requirements or to the new way. There's another thing that I like to reflect on. I saw a few people taking pictures of the diagram, so I gather either you find it pretty or interesting or something like that. I think it helped me a lot in its moment when I did it because it helped me identify problems. In fact, I already had suspicions about that module, and this kind of confirmed that's what we need to attack next. It has one problem, though. I had to do it manually. I had to go to the logs and get all the stuff and do analysis manually and put it on a spreadsheet and then do this PowerPoint by hand, checking the colors from Excel, etc. Which took me like a good day or day and a half. Now you can do that, but if you do that, that means you're not going to be able to do it very often. You can do this exercise maybe once a month or once every 2 months. Ideally, same as with the continuous integration idea, you'll do this after every commit. So after every commit, you'll recheck, okay, what's your status? But to do that, you need to automate everything because manual takes a lot of time. I've been looking around for different applications that kind of do something like this, and I haven't found any. If you have, please let me know because I'm very keen to know. Because I didn't find it, I thought of automating the build analysis myself. Now, this is possible. I thought it was easy. It's not really that easy, but it's possible because most continuous integration systems provide an API. So I started this with Jenkins and started it with CICD. I had a bit of play with it, and they have a very nice REST API. You can gather the data that you need. The calculations aren't particularly complex. After all, we're talking averages and things like that. It's not rocket science. And there are graphical tools available. Now, the fact that they are available doesn't mean they are easy to use or that when you use them are going to be pretty. So in fact, I gave it a go. That's what it kind of looked like. So that, again, is from a real system. And it draws the stuff by itself. You can check it out. It's out there. So for instance, here's a part where it identified the dependencies and it drew it. This kind of hairy-looking bit is also dependencies, but was like a very basic module and a lot of things depending on it. And because it depends, so many things depending on it, and I couldn't draw the graph properly. But then this gave me the idea of it can't be done. It's just a little bit hard. So I started it. If anybody wants to give it a shot and take a look, then you're welcome to it. It doesn't do much. Things that I like to do next are basically this, add the size and support for the CI systems, etc. Because at the moment, it just does the color, but it doesn't do the size. It doesn't do much. It's more like an idea of what you could accomplish if you did something like this. But well, I thought it would be fun to show you. to share it with you. So, the last thing I wanted to mention is, this is all very hard, right? You can take a look at that code that I produced, and you can see that it's not very nice because I didn't know JavaFX, and it does very little despite the hours that I put on it. So, this is a Formula One wheel drive, driving wheel, sorry. You can see it has many buttons and displays and knobs and things to set up. The wheel itself costs about $30,000 to produce, and that's just the wheel. And you may wonder why. Well, here's the thing. Formula One cars are ridiculously fast and ridiculously high performant. The reason they're so fast is because they measure a ton of different things, and then they provide all the information to the driver so that the driver can adapt. So they will measure things like the temperature of the tires. They will measure the weight of the car as it's consuming gas, and therefore it weighs less. They will measure the wind from different directions and how that affects the aerodynamics of the car, etc., etc. And then the driver can adapt to that. And then that way you can have a super fast car. But the morale of here is, if you want something fast, you need to measure a lot of things. You need to be able to respond to all the things that you're measuring. And most importantly, you need to build the tools that give you all that information and all the reaction capabilities. And that takes time, and it takes effort. Thank you.